Hello and welcome back to Calculus 3, section 13.2 on vectors in 3D. Pretty much everything we talked about in last section is going to be carried over except the direction, which is not friendly in third-dimensional space. And the coordinate system now is third-dimensional, meaning you have x-axis, y-axis, and z-axis. Now, you live in third-dimensional space. In order for you guys to see these things fast and easy, you should use the corner of the room. The wall with the clock, with the door, is going to be your x-axis on the floor. Along the wall where the board is the y-axis, and you have a z-axis in a corner going up towards the ceiling. The reason why we need that is so you can visualize stuff, and you can visualize stuff in 3D. And there's some really cool, if you own any of the VR sets, try to go into that place where you can actually draw 3D around you. You know how you can buy the spray, the paint spray, right? And you spray paint stuff. Well, imagine the spray paint that when you do this in the air, it like leaves that 3D around you. VR allows you to spray paint and actually leave the stuff as a foam looking or whatever around. You can draw anything, which is awesome. So now, what do we have? Well, we are jumping into 3D, and we are going to talk about coordinate systems. X, Y, Z, third-dimensional coordinate system. Guys, this one is going to be called right hand, and this is the one we are going to use almost all the time. But there's also a left-hand one. So why is this one called the right hand? As you take your right hand with the thumb up and you wrap around z-axis, your fingers are going to wrap around and they're going to hit the x-axis first and then y immediately. And then there is a whole 270 degrees to go. So on this side there is 270 degrees, on this side there is 90 degrees. So this is how you know it's a right system. When you grab it around z-axis with the thumb pointing up into the z direction, up, your fingers wrapping around hit x-axis and then 90 degrees later hits the y. The left, so this is the right hand system, and this is the one we use. Now the other one also exists, and you have to be careful because you know your AutoCAD or something could be set in a different system, so you have to be careful about these things. He has Y and then X and Z. So now this is the left hand, because now you have to use your left hand to wrap around Z, and then your fingers hit X, and then 90 degrees later they hit Y, and then you have to go 270. So if you try to use your left hand on the first diagram, when you wrap around, right, you see that you hit Y and then X, because 90 degrees. And if you use the right hand, you hit X and then Y between the 90s. So that's what's important. We can also use isometric view. Sometimes this is going to be a better representation. Guys, we need to represent third-dimensional surfaces and objects in 2D. So of course you can't do it because you're one dimension short. Which is why I mentioned that if you do have a VR set, you can do these things in VR, and it's amazing. So these are the systems that we are using. Now, the way this works is, for your 2D system, you had 4 quadrants, and they were labeled 1, 2, 3, 4, counterclockwise, and you know where they are and all that good stuff. Now, you have octets. These axes will create planes which cut the space. So you are talking about 8 rooms. 4 on the bottom floor and 4 on the top floor. So 8 rooms. You get 8 octets in this space. Now, I think they have a very nice picture of that in the book, which I'm going to show. The book, obviously, there's a reason why this thing is $1 million, because they, as you can see, explain the right hand and all that good stuff. And here is the diagram for so here's the diagram that you have. And this is search, right? What happened with my zoom option? Oh, zoom option, there we go. So if you look at this diagram, I hope you see the blue plane, and you can think of that plane as the floor in this classroom. And if we are to sit in this first octant over there as our classroom, then there is one classroom next to us, the other classroom on the other side of the wall, the other classroom there, and then 4 classrooms underneath. The space is divided in 8 spaces. Now, each one of the colored planes, you have the brown one, the blue one, and the green one, represents a wall or a floor or a ceiling for the bottom ones. And you can see that the floor and the ceiling is XY plane. Guys, that's your 2D realm that you know so far. So the blue plane that contains X and Y axis is 100% of what you have dealt with so far. All of the graphs that I drew earlier, they live in that blue plane. Now you put up these walls, the green one, and those are the planes. So you have the XY plane, which is the floor, the XZ plane, which is the brown wall, and YZ plane, which is the green wall. So those are the ones that you guys have, and the third-dimensional space now is going to use the 3 dimensions, x, y, and z, in a point to get the location. All right, so now, how do we get location and other stuff? So, first of all, 3D will be noted as R3. So that's the way, because now you have 3 real number axes that are intersecting at 0, 0, 0 at 90-degree angles. You have x1, you have x, y, and z, and each one has positive and negative numbers and all that stuff. So each one of those is from negative infinity to positive infinity, all real numbers, and then you have 3 of them, right? So we'll just call it r cubed for ease of notation. All right. Let's graph a point, say 3, 4, and negative 5. 3, 4, negative 5. We are going to draw the right coordinate system, x, y, and z. We are going to walk 4 units down x-axis in a positive direction. If you have a negative x, you have to go on the negative x-axis, but we don't have it, so I'm not gonna include it. Now, you need to go 4 in y direction, which means you need to have the line that it's parallel with y, that it's going to go 4 units. 1, 2, 3, 4. So this point is 4, 0, 0. It's just a point on x-axis, y and z are 0. No, sorry, 3. Ah, you should say something when you see the stuff is wrong. You see over here that I have x3, so it should go 3 units. 3 units, there we go. Much better. And now, parallel align to y, and you're supposed to go 1, 2, 3, 4. So this point here is 3 for x, 4 for y, and 0 for z. We haven't done anything for z yet. And now, parallel line to z, but because we have to go 5 units down, we'll draw the line straight down, because that's parallel to the straight z axis. And you will count 1, 2, 3, 4, 5 on the bottom. So now this is 3, 4, negative 5. Now you can erase everything else, but it's kind of cool to know, right, which way you got it, so just leave it there. So you count positive or negative x, then you draw a line parallel to y, and you go from there. Now, can we do this in isometric view? Of course. You will go 1, 2, 3 units on x, then you have to draw parallel line to y, go 1, 2, 3, 4 units on y, so this is now 3, 4, 0, and then parallel line to z to go down 1, 2, 3, 4, 5, and here is your 3, 4, negative 5. So getting these values is not terribly difficult. You just have to be careful which axis you are on, and every time you are counting, you have to be parallel to the original axis. Now, as soon as you are able to graph a point successfully, you can immediately stretch a vector to it and call that vector u, and then your vector u is going to be spiky brackets 3, 4, negative 5, and ta-da! We are talking about 3D vectors. Yes?
How do you know to use the right hand?
We are always using the right hand. That's the deal. Unless you see something done. So in class, we will stick with the right one, but you might run into your AutoCAD drawings or engineering drawings, depending on, right, work with mechanical engineering, civil engineering, or you all have technical drawings. Just need to make sure, is it the left or the right coordinate system? So the answer is it's convention. Good. So now, your vector u is going to be ux, uy, uz. It's going to have 3 coordinates. You get vector u if it's between the points P and Q. Again, terminal minus initial. So uq minus xq minus xp, yq minus yp, zq minus zp. Magnitude, which is the u absolute, is you're adding z squared in the mix. We don't deal with the direction. Direction depends on what you need. You see, the direction is very tricky, guys. You have to use trig and you have to use whatever fits. There's no formula for direction here. Because you have two angles that are important, right? When you have something in the corner, there is the angle to each of the planes. So you have to drop the shadow on XY plane and get the angle towards the, right? So I'm going to illustrate this, but we don't deal with it. So you don't really need it now, but I'm going to show it anyway. So let's say you have X, Y, Z, and you have a vector U. Now, magnitude, easy. We're done, right? Direction. You see the direction. You shine the light above, which would give the image of that. So this is a shadow of that vector. Now, that's in XY plane. So since this is in XY plane, you have your angle theta in XY plane using your tangent, right, with the XY to come up with whatever that angle is. And then you have an angle with a z-axis here. We can call that angle phi, which when you go phi to the shadow is 90 degrees, but then there will be a point where this one intersects. So the direction is very tricky. It has to be given at least two angles, right, for each one of these direction vectors. So it's not an easy thing to determine, and we don't have a use for it. I mean, clearly you can find a lot of use for it, but there's no use that we particularly use it in our course, so we don't stress too much about the direction for 3D. So now this picture is going away because, again, don't really need this stuff. So we talked about the basic notation. Oh, by the way, you can have this as UXI, UYJ, UZK, IJK unit vectors. So we have the notation for vector U as a vector notation or the component notation. We also get the vector by subtracting coordinates, the terminal point minus initial point. Magnitude, you just add the z squared in the mix. The blue properties are the same. As in R2. And what else do we have? Something else. Add, subtract, scalar multiplication, the same. So add, subtract, scaling is the same as in R2. So you just need to, add an extra component. So let's say you let vector U be 3, -1, and 6, and vector V to be -2, 8, and -3, whatever. Compute 3U minus V. So you just plug in, right? It's 3 times 3 negative 1, 6 minus negative 2, 8, negative 3. So this is going to be 9, negative 3, 18. And now I'm going to distribute the minus. So plus 2, negative 8, 3. And now you're adding. So 11, negative 11, 21. Ta-da! That's it. Unit vector. U hat is the same formula as before. This works in any dimension. So it's the same unit vector as before. And now they have the introductory talk about planes, and there is also introductory talk about surfaces, because they give you the equation of the sphere. Later on we're going to have ellipsoid and a whole bunch of other things get into our course. Now, sphere, which is a ball. So sphere object it has a radius r, and when you have any vector of length r touch any vector of length r that it's pinned at the 0, 0, 0 origin, that vector will reach everywhere around itself to trace the sphere, because every point on a surface of the sphere is the same distance away from the origin. It might be a shock to some, but the planet is actually round, and there is a very good reason for it. Every particle of the planet wants to be in the lowest energy state. For humans, that's described as laziness. It's just natural. You want to be in the lowest energy state, which means doing nothing, and your body is still using a lot of energy to just run itself. You can go and do the research of how much energy is required just to run basic operations as breathing and heart and maintaining all the organs functional. And then on top of that, you add labor and work and stuff. So for the planet, the reason why all of the objects are round and not flat is because each particle wants to be in the lowest energy state, and the closest distance to achieve that is to arrange themselves so that they are the closest they can get to the center, which is what forms a ball, which is why every single object you run upon is, right, in space, is spherical. So you have a radius r, and you are in the 3D XYZ system. So the equation for this, centered at the origin, is x squared plus y squared plus z squared equals r squared. This is your equation for the sphere, and this is at 0, 0, 0, at the origin. Now, we are already evolved to the point that we know that our planet is not the center of the universe, which means that the center of our planet is not in the center of the universe, and nothing revolves around our planet. You should immediately extrapolate that to you. Your life will exponentially get better as soon as you realize that nothing revolves around you. You're not special at all, even though everyone tried to make it like it is. You're not. The sooner you realize that, everything else will go better, including interviews, all right? So we can center the ball anywhere we want in the universe. So center at, let's say, ABC point in the universe will give you x minus a squared plus y minus b squared plus z minus c squared equal r squared for the sphere centered at ABC. Now for the circle we had h and k and stuff like that, but whatever. All right, cool. So that's the story of the sphere. There is really nothing else to say about it. It's just an equation that has the z component added to it to upgrade circle into a three-dimensional object, which is a sphere. So we're done with that. And I just want to talk briefly about the walls, which are those basic planes. So you saw them color-coded in that textbook example. I'm going to draw now, and let's do it this way. There we go. So we have our right coordinate system x, y, and z, and it also shows the negatives in this case. And now I'm going to first, let's do the floor. So you draw parallel lines to y and parallel lines to x to create the plane, which is the floor. Now, since if you draw this too close to the edge, just move it like that. So this plane, y-axis, live in it. So that's your xy plane. And I will frequently refer to it as a floor. If you want the xz one, let's go with orange. Yeah, I saw the lag. Well, we're done technically. I'm just going to draw this and we're done. Thank you. So this plane is the xz plane. Guys, that's that wall over there. Because we said your x-axis is on the floor, where the door is, and your y-axis this way, because if I am to grab the z-axis in the corner, my fingertips hit that wall first, which is x, and then 90 degrees later, they hit this wall, which is y. So it's a right coordinate system right there. So your x wall is the wall with the clock. Your y wall is the y with the wall with this. But it's actually xz wall because it has the x-axis and the z-axis. So that's xz wall, that's the yz wall. And now the last one is the yz, which is the board wall. So we draw that one. And we are done. The homework is open for you to enjoy. You have access to the syllabus to get the code if you want to use my MATLAB. I encourage you, but then again, it's up to you. What color should we go for here? How about we go green, huh? So That's the YZ plane. So YZ plane. Note that whatever I'm drawing, it's always parallel to the axis. So YZ plane, the top and bottom are parallel to X, and the side ones are parallel to Z. And then when you go to the orange one over here, it's parallel to X and parallel to Z. And in the top, parallel to X and parallel to Y. So the calculations and everything else pertaining to vectors is the same. You're just adding a Z component, and we don't worry about the direction. We are going to talk about direction later, but in a little bit different light. When we do spherical coordinates, you still have time to enjoy life until we get there. We'll have fun. All right, guys. So that's that. Bye.